There's 5 motion quantities: distance, displacement, speed and velocity, and acceleration. What's distance? Well, distance we're already very familiar. Distance is the length of a path, and it's measured in meters. So what's displacement? Well, displacement is known as the vector equivalent of distance, and that means that it is distance in a specified direction. Now, you may know that vector quantities all have a specified direction. So displacement is an example of a vector quantity. It's the vector equivalent of distance. That means its units are also in meters. Now, this is the definition which you should quote if you are asked to define displacement. But let's have a closer look at what it really means. So we'll do that by an example. Supposing I have a snail. Now, here's a snail. And let's say that the snail has just travelled on a wiggly path and it's left a slime trail. Now, if we were to say, how far has the snail travelled? Well, that's the distance that it's moved, and that would be the full length of this trail, all the way as long its wiggly length like that. This is the distance travelled. So if we were to then ask, what about the displacement of the snail? Well, in its current position here, its displacement from its start point is the direct distance from start to where it is now. And the direction of the displacement is simply the direction from start to its current position. So this is the displacement. As you can see, both of these would ordinarily be measured in meters, although in some cases we use centimeters, which would probably be more reasonable for the length of a slime trail of a snail. But we also use kilometers and a variety of other measurements of units of distance. Okay, what about the direction of the displacement? Well, how is it expressed? Well, in some cases we might express the direction as an angle perhaps to the horizontal, or perhaps we would do a bearing from north, or sometimes if it's just simple left-right motion, we could express the direction as left or right, or sometimes plus or minus. So the answer is, it very much depends. Sometimes we use the points of the compass, north, south, east, west, but not always. Moving on now, speed and velocity. Now, you may have guessed, velocity is the vector equivalent of speed. But what is speed exactly? Well, speed is the rate at which something moves. It's how quickly it moves. And that means we define it in the following way. Distance travelled per unit time. Now, what does per unit time mean? Per unit time means basically per second, since seconds is our usual unit for time. So supposing we had a buggy travelling along a certain route, travelling at a certain speed. We use the symbol V for speed. Now let's suppose it travelled a certain distance d along the road, and we measured its time using a stop clock, and we found the time to be time t. How fast was it travelling? Well, the thing is speed can change during that time. It could speed up sometimes, and sometimes it could slow down. So using the quantities of distance and time, we can actually only calculate average speed. And we do it by dividing the distance travelled by the time taken. So I'll write the formula here. Average speed equals distance divided by time. Let's put a box around that. Okay, so as an example, supposing our buggy travelled 20 metres and it took 5 seconds to go that distance. So how fast was it going? Okay, well, we need to work out the distance that it travelled per second. So if it travelled 20 metres in 5 seconds, then each second it would have only travelled 4 metres. And so if the distance travelled is 20 metres, and the time taken for that was 5 seconds. On average, its speed would have been 4 meters per second. And that's how we work out its speed. Using the formula, we simply do 20 divided by 5 gives us our answer of 4 for the average speed of the buggy. I'll add units to the formula, just in case you want to refer to it later. That's in meters, that's in seconds, and this is in meters per second. Now, occasionally, because it's very common in everyday life to use the units of kilometers for distance and hours for time, sometimes we use the units kilometers per hour for speed. So in that case, if you're dividing a distance in kilometers by a time in hours, then you'll get kilometers per hour. Okay, what about velocity? So velocity is speed in a specified direction. However, annoyingly, we don't normally define it like that. The way we define it is rate of change of displacement with time. However, the formula we use for velocity is essentially the same as the formula for speed, but instead of distance, we replace with displacement. As for the direction of the velocity, it's the same as the direction of the displacement. So in the case of our snail here, supposing it travelled a distance of 1 meter, and let's suppose it traversed that distance in 200 seconds, say. So I'll put here t equals 200 seconds to go that far. So how fast was its speed? Okay, well, again, we can only work out its average speed. Its speed may have changed slightly along its path. But to work out its average speed, we would use this formula, and we would do the distance travelled divided by the time taken. So 1 meter divided by 200 seconds, which I believe should be 0.005 meters per second. So if I do my calculations here, average speed equals distance divided by time. 1 meter divided by 200 seconds equals 0.005 meters per second. Now, 0.005 meters might be better expressed in centimeters, and it would be 0.5 centimeters per second. So that's how far it went on average per second, and that's what we use to express its speed. Now, what about the velocity of the snail? Well, again, we can only work out its average velocity. Maybe I'll do that one over here. Average velocity is displacement divided by time. The formula looks the same if we write it in symbols. So what's its displacement? Well, I didn't decide yet, so let me decide. Let's suppose it's 20 centimeters or 0.2 meters. So in here we would put 20 centimeters or 0.2, and we're going to divide that by 200 seconds again. Okay, so what do we get? Well, the answer is going to be 0.001 meters per second, which is 0.1 centimeters per second. Okay, and the direction of it is the same direction as the displacement, which I haven't expressed here, but we can see the direction from the arrow clearly. Now, let's have a look at acceleration. Now, acceleration is usually when an object is speeding up, but actually in physics we have a slightly broader definition. Acceleration is the rate of change of velocity with time. Let me write that first. Okay, so as you may have gathered from the definition, it's related to changing velocities. And if an object's velocity is changing, that means it's accelerating. So how can an object's velocity change? Well, it could be speeding up. If the speed is increasing, it means that the velocity is increasing too, and that means accelerating. But it could also be if the speed is decreasing, slowing down. Slowing down we sometimes call deceleration, but it's still considered an acceleration, and if the object's moving forward, that's a negative acceleration, that's a deceleration. But there's a third case. An object is accelerating even if its speed is not changing, if its direction is changing. Because acceleration is related to the change in velocity, even a change in direction counts as an acceleration. Now, when it comes to calculating acceleration, we don't actually worry at first about changes in direction. So let's have a look at how we might calculate the acceleration of an object which is changing speed. So first of all, I'll give you the formula for acceleration. I'll write it over here. Acceleration equals change in velocity divided by time. Now, this symbol here is the Greek symbol delta, and it means change in. So when I write delta v here, it means change in velocity. And since we're not worrying in this case about any changes in direction, it's essentially the same as change in speed. Now sometimes we will write that like this, v minus u divided by t, where v is the final velocity of an object, u is its initial velocity, so doing v minus u gives us the change in velocity, and then that's divided by time. So let me put a box around that. And let's just clarify the units for acceleration. So changes in velocity are in meters per second. Time is in seconds. And if we're dividing meters per second by seconds, we end up with meters per second, which is often written more succinctly as meters per second squared. Now that sounds very odd, but it will probably make much more sense when we do an example. So let's do that now. Imagine we've got our buggy again, travelling along a straight road, so no change in direction. Here it is at time t equals 0, so that's at the start. And here it is at time t equals 16 seconds, say. Now, I'm going to say initially it's going with speed, beg your pardon, should use a u for initial speed, 1 meter per second. And by the time it's speeded up for 16 seconds, by that time it's reached a new speed of, I'm going to say 9 meters per second. So it's speeded up from 1 meter per second to 9 meters per second, and it took 16 seconds to do it. So to give an idea of how quickly it's speeding up, we work out on average what's its increase in speed per second. In other words, how many meters per second is it increasing each second? Well, its increase in speed here is from 1 to 9. So that's an 8 meters per second increase in speed. And that took 16 seconds. So an increase of 8 meters per second in 16 seconds is a 0.5 meters per second increase per second. Does that make sense? So it increased by 0.5 meters per second every second for 16 seconds and ended up at 9 meters per second. Let me show how you do that using the formula. So acceleration equals change in velocity, or change in speed in this case, same because there's no change in direction. The final velocity is 9, the initial velocity is 1, giving us a change of 8, and the time taken for that change is 16 seconds. So 8 divided by 16 is 0.5 meters per second, or meters per second squared. Now, if the speed is slowing down, our final velocity would be less than our initial velocity, and that would give us a negative answer. So as I said earlier, if the thing is travelling forwards and you're getting a negative answer, that means it's deceleration. And you could express it as a negative acceleration or simply a deceleration without the negative sign. Finally, I want to look at a case where the object's direction is changing but its speed is not changing. A frequent example of this is for objects which are moving in a circle. So a nice one to do might be us. We're moving in a circle around the sun. We're on the Earth and we're moving around the sun. So let me draw the sun here, and I'll draw the Earth in its orbit around the sun. Woohoo! Totally missed the center of the circle there. In our travels around the sun, the speed of the Earth remains largely the same, but our direction is continually changing. And so we are considered accelerating. And if asked the direction of the acceleration in this case, it's acceleration towards the center. This is an example of centripetal acceleration. Centripetal means towards the centre. So this is just one example of where an object is changing its velocity without changing its speed, merely by virtue of the fact that its direction is changing and velocity is a vector quantity.